So we have a field of rotations of spatial Dreibeins in M4. That's what we treat. And then we have a Lagrangian, which looks like this. So the rotations we describe by quaternion with Q, and we derive the tangential field gamma mu and the curvature tensor R mu, and we get a Lagrangian. That's what is the model. So very simple, only 3 degrees of freedom in space-time. And I wanted to go, yeah, I mentioned again that we have 3 topological quantum numbers here. So we have pi 3 of set of S3, which is spin, pi 2 of S2, which is the charge, and pi 3 of S2, which is the photon number. This is what I told before. And now we come to a more difficult problem. This is Dirac equation. How to get to the Dirac equation? Let me start. Where is it? Map. Yeah. We had 4 types of solitons, differing by charge. So electron means vector going outside here and here. This is, say, a model for electron, and vectors going inside. This is a model for positrons. Now I have to go to quantum mechanics. Of course, I cannot derive what is the mechanism of quantum mechanics. Up to now, everything was classical. So in order to go to quantum mechanics, I have to follow the laws of quantum mechanics. And one of the laws is that different states correspond to vectors in Hilbert space. So I have 4 Dirac spinors corresponding to these 4 states. And this corresponds to vector in Hilbert space. So I'm now in Hilbert space, and in Hilbert space I introduce an operator gamma 0, which is the diagonal matrix 1 and minus 1. And I define the Hamiltonian H0 acting on this vector psi, so on a free vector psi 0. So this is static electron or static positron is this gamma 0 on psi 0. So in this way I respect the signs of the energy. You see, -1 for positron. This is positron. So I have the eigenvalues -1, and for electron I have the eigenvalues +1 for gamma 0. And I multiply with m0 c0 squared, so with the energy. So in this way I get Dirac equation I define Dirac equation for a free particle, for a free non-moving particle. I have to go to moving solitons simply by Lorentz transformation. So from this gamma m0, I multiply with the velocity v0 and v, and get the d mu. And d mu is of course squared, the energy, the mass squared. So this is nothing else than these triangles that you see here. So gamma m0 c0, this is the energy. Gamma m0v is the momentum, and the squares subtracted gives you, according to Pythagoras, the mass squared. The same you can write with the square roots here on the right hand side, and this defines an angle omega, which we need later for fully Woodhuizen transformation. So we see that cosine omega is the hypotenuse divided by the neighboring catheta. This is m0 c0, and this gives you 1 over gamma. And the sine of omega gives you the v over c0. So we remember these equations because we need them now if we do electron-positron mixing. I have used the invariance of the center transformations that the spin up and the spin down can be, the electron, the positron, the spin up can be mixed. So I introduce a mixing matrix I, which is off diagonal 2 times 2 matrices, 1 and minus 1. I square is minus 1. And I can make a rotation in this space e to the I omega sigma half. This is cosine omega half plus this matrix I times sine omega half, sigma sine omega half times a omega. And I multiply with this matrix u omega in this 4-dimensional Hilbert space. I multiply this I omega with gamma 0. And we see immediately that you have, if you commute it with gamma 0, you get here u omega dagger. And this I use here in order to make a Foldy-Woodhausen transformation. I start from the Hamiltonian of the resting of the particle at rest. If I move it, then I have a gamma 0, m0, because the mass is increasing. And now I make this Foldy-Woodhausen transformation. H omega is u omega, h u omega dagger. And this is because of these commutation relations which we saw before. This is h u omega dagger, and this gives you h u omega dagger squared. So in this h omega you can calculate. This you see this is nothing else than this u omega here. This is this exponential here. And this, of course, is cosine omega plus gamma e omega sine omega. And you see now that the h omega goes simply to this term m0 c0 times gamma 0 plus gamma 0 gamma I pi c0. And this looks now as the Hamiltonian of the Dirac equation. So you have, if you multiply this equation with psi, you get gamma mu p mu on psi is m0 c0 psi. So I repeat, I interpret the 4 solitons as vectors in Hilbert space, and I insert the velocity dependence of the mass. That's all I need. And then I do this Foldy-Woodhausen transformation with this angle omega in order to arrive at the Dirac equation. So I have the free action of the Dirac equation, C dagger, gamma mu p mu minus m c 0 psi. So this is the free action. And now I have to introduce the interaction with electromagnetic fields. I need the interaction term in the Dirac equation of this form. And for this I have to do 2 steps. I have to make a dual transformation, and I have to go from the non-abelian f mu nu. You remember that I have a non-abelian curvature tensor to the abelian f mu nu. And this we did in order when we went from the extended solitons to point-like solitons, then monopoles to point-like solitons. So this is, we need the a mu, but we have the c mu. And the c mu is connected with the gamma mu. This is the dual vector potential. So I do these 2 steps. I reduce the extended monopoles to point-like solitons, and I make a dual transformation. This means I go from this field strength tensor to the dual field strength tensor. So in this field strength tensor, f mu nu, I have now to represent by d mu a nu minus d mu a mu, by the abelian definition of the field strength tensor in electrodynamics. Action theory, I separate the field strength tensor in the in this f mu term in mu with the Lagrange, yeah, and I have this new external introduced here. Sorry, I'm now on another computer. Do you hear me?
Oh, yes.
Yes, it's okay.
We can hear you. We can hear you. Yeah, so
Hello,
yes,
do you hear me?
yes,
Yes,
we can hear you.
you.
Yes.
Hello,
Yes,
do
hello,
you hear
hello.
me?
Yes. Can you hear us?
I lost.
Please reconnect.
Hello, now I hear you. Sorry, I'm on another
Yeah.
computer.
Yeah, so because sometimes if there's a problem, sometimes it's good to connect and reconnect, whatever. But
I'm
I
another.
cannot see your slides. I cannot see your slides.
Yes, here you cannot. I have to switch on my slides here. But do you see the slides on the other computer or not?
Now, before it was, but then your presentation was frozen.
Yes.
So I decided to reconnect by myself and now I see you have similar problem. Maybe you should reconnect. I don't know. It's up to you.
I start again my talk. Wait a minute. And then I have to try.
Sometimes the best is to stop connection and redo. Sometimes it's the best way. You know?
Computer was frozen. I'm now at another computer. I have two computers on because of problems before, so I started a second computer. So I try now screen sharing.
Yeah, but doesn't work. It shows the screen sharing process is starting to take place, but there's no result. So maybe again, you can try to do it. Oh, now I see yours. Yeah, I see your slides finally. So just make it bigger and just maybe Ctrl ++ or whatever. There is some comment to do it. Yeah. Yeah, so we can see your slides. Can you make it the half of the screen, because it's almost, yeah, so I think it's a good starting point. Yeah, so we haven't seen the Sine-Gordon model yet, I see. Yeah, so slides are seen okay. Can you magnify it somehow, because it doesn't take the whole screen? There is, I don't know. Yeah, I can see you underline text. That's fine.
So Faber, we cannot hear you.
Faber, you have probably muted microphone, probably. Professor Faber. Hello? We do not hear you.
You don't hear me. Okay.
Now it's okay.
Now
I think you can proceed, but can you make it bigger? The slides slightly bigger than they are.
Right. Yes. So like this.
Oh yeah, but just the bottom part. Now it's acceptable for us, let's say, because before it took the whole screen, but I don't know, now it's you scroll it. It's still okay. I mean,
Wait a minute. Oh, now it's going on. So here I
I think you can move it to the upper left corner.
So it's working like, wait a minute, I'm doing. Just a minute. So now it's working. So like this.
yeah, just even make it bigger. Yeah, it's okay right now. I think it's acceptable for us.
Largest height. Now.
Okay, so probably it's good if you proceed.
Yes. Okay. So I try to separate the action in having two terms for f mu, an external field and an internal field. And with this way, I get the free action, which I defined before, or derived before. Then I have the internal, the interaction term, which gives you the two contributions of f mu. And I can here make the partial integration and shift the d mu from the d mu a nu to the f mu. And then I can insert in the d mu f mu the current J nu. And this current J nu is, of course, psi r gamma nu psi. And in this way, I get three contributions for the psi bar psi. So here I get this first part, which is the 3. Here is the interaction part. And this is the external contribution. Okay, so in this way, I'll get somehow the Dirac equation. So what I needed is inserting Hilbert ray vectors for the 4 solitons. And then I had, of course, to accept that P mu is written as a gradient. So I have had to accept the canonical commutation relation of quantum mechanics. This is the 2 steps which I need in order to derive the Dirac equation. So now I come to some other phenomena which may be interesting. This model can find some possible mechanism for inflation. And at the Big Bang, or after the Big Bang, it may happen the following, that we started with a trivial Q field as a trivial field, which wherever the whole field in the universe was a unit matrix. And we have this potential energy lambda, which is proportional to 1 over R0 squared. And there can be a transition from Q equal 1. This is the north pole of S3 to the equatorial plane, where the potential energy lambda is 0. So at the north pole, the potential energy is 1 over R0 to the 4. R0 is the size of the solitons. And we make a transition to lambda equals 0. And we can calculate the energy density, which I have here. in the state with unit matrices. And this is simply the prefactor of the Lagrangian, alpha f h bar 0 over 4 pi times the value of lambda, which is 1 over r0 to the 4. And this gives this equation, and we can insert in this expression the value of R0. R0 was 2.2 Fermi roughly, and this gives you 4.8 keV per Fermi to the cube, or 7.7 10 to the 29 joule per cubic meter as energy density release in this inflation. So this is one mechanism which you can have. Another point which interests cosmology is the cosmological function. This is dark energy. So I have a potential energy term, lambda. And this is, so to say, a cosmological function, not a cosmological constant, but a cosmological function. So lambda of x depends on the position in space compared to solitons. In the internal of solitons, lambda is positive, and in the vacuum, it's 0. So the cosmological constant is given from Planck data as 4.69. Of the critical cosmological density, ρ0 times c squared, this is 4.9 GeV per Fermi cube, per cubic meter. And the prediction of particle physics is the well-known number, well-known, but famous number, which is the worst prediction of history of physics, 10 to the 121 GeV per cubic meter. In my model, you get, due to Derrick's theorem, you get for this cosmological function 1/4 of the mass of particles is going to lambda. I didn't speak about Derrick's theorem. You see there that we have a contribution to curvature energy and a contribution to lambda, to the potential. And this is in the ratio of 3 to 1. So in order to get this energy density of 4.9 critical times 0.69, I can ask how many nucleons do I need in the universe? And I need roughly 14.5 nucleons per cubic meter in the universe in order to explain the value of the cosmological constant. This is not a very unreasonable number. Yeah, this model has also non-topological excitations. I told you we have 3 topological quantum numbers, so we have topological solitons. But further than that, we have other non-topological solitons. It can be, for example, waves in n and waves in this angle degree of freedom, which I called alpha. Yeah, I have here some discussion about some alpha degrees of freedom. I don't want to enter. Maybe interesting is a final conclusion comparison to Maxwell electrodynamics and differences to Maxwell electrodynamics. So what is agrees with Maxwell electrodynamics? The Lagrangian is Lorentz covariant. This means the laws of special relativity are respected. I remind you on the comment by Spolsky, where he told that extended electrons don't agree with special relativity. It's clearly seen that my Lagrangian is completely Lorentz covariant, and this claim was wrong. So we have charges as sources of Coulombic fields, and they fulfill the Gauss law. The Gauss law is purely geometrical. Remember that my solitons can be in the limit of R0 to 0 go to singularities, and the singularities have world lines. And if you have a sphere around such a singularity, you feel that the flux is coming out of the singularity. For extended solitons, of course, you get the Gauss law as soon as the sphere is large enough compared to the size of the soliton. So charges interact via a field which is decaying like 1 over r squared, and the charges feel Coulomb and Lorentz forces. I have explained that I have a local U1 gauge invariance, And even it's not only derived, yeah, it's not only stated, but it's derived. And then I have shortly discussed that I have two massless excitations, two Goldstone bosons, which are left and right-handed depolarized photons. So now we get to next. So there are differences to Maxwell electrodynamics, and of course one has to check if this maybe some reason to reject this model. So one difference is that electric charges are quantized. So there are no other electric charges than multiples, integer multiples of the unit electric charge of the electron. They are quantized like the magnetic charges of Dirac monopoles, since charge is a topological quantum number. So this, of course, we like this difference to Maxwell electrodynamics. Maxwell did not have problems with singularities because he was thinking of extended charges. The problems appeared as soon as in quantum theory or quantum field theory, one realized that one should describe electrons as point-like charges. And this leads, of course, to the problems with singularities, which I explained in the beginning, which have to be removed. And let's finally do some interesting, nice conclusion that the electric charge is not a constant, but depends on the transferred momentum. So by topological construction, we have mirror properties of particles. So if we have the particles, we have antiparticles. Of course, also welcome. So the mass of solitons is completely due to field energy and finite. I would also say this is positive. The self-energy of charges is also finite and does not need regularization and renormalization. Charges and their fields are described by the same degrees of freedom. So there is no difference between electron and its field. They are described by the same 3 degrees of rotational degrees of freedom. Yeah, it's an interpretation as spatial Dreibeins, which are rotated in space. Gauge symmetry is a geometrical phenomenon, and its basis changes on S3. Spin has the usual quantization properties and combination rules. It's also nothing in Maxwell's theory, which is from quantum mechanics, and it's coming from topology. We have 4 basic configurations of solitons with the quantum numbers of Dirac spin laws. So there are further distinctions. Solitons and antisolitons have opposite internal parity. Solitons are characterized by a chirality quantum number, which can be related to the sign of the magnetic quantum number. Spin contributes to angular momentum due to internal rotations. The canonical energy momentum tensor is automatically symmetric. Static charges are described by the spatial component of the vector fields. Moving charges by nite time-dependent fields. This is the dual transformation which I have on the minute. So the radial dependence of charge is given by the finite size of solitons. It leads to the running coupling. Yes, locally you want gauge invariance, I mentioned already. Photon number is the Gaussian linking number of fibers of S2. The photon number changes by interaction with charges. So of course, if dipole the case of positronium the case is of course in this model a very complicated dynamical process. Photons have a linking number. So something which is some fibers which are linking have to separate from the dipoles. So if such a photon which has a linking number interacts with the charge, then it can change its spin. So then rather unexpected is that spin and magnetic moment are not static properties. And these are dynamical properties. I have many discussions with Jarek on this point. He prefers to have an internal clock and an external magnetic moment. My model does not have internal clock. Everything is static for a static soliton. Nothing is moving. The spin comes if the particle interacts with another particle. if they rotate around each other from the angular moment, from the orbital angular momentum, or from the changing external fields from a B field. A B field is time-dependent oscillations of n vectors, and the soliton reacts dynamically on this changing external magnetic field. So not only the spin, but also the magnetic moment is a dynamical property, not a static property. Of course, it's difficult to calculate, and I wasn't able to do that up to now. But the mechanism is there. It's the question to prove it by numerical calculations. I don't think that one can do this analytically. So there is a property which in the first moment looks not very nice. This is that electric and magnetic fields are perpendicular to each other. I didn't discuss it. Because in experiment, we have no problem to make parallel electric and magnetic fields. And this could look like a discrepancy of my model to nature. But there's also an excuse, and the excuse is that this is only at the macroscopic scales, that the fields can be parallel. They could be at small scales, in femtometer scales. They could be perpendicular to each other. Like we know from electromagnetic field in the vacuum. Everything is vacuum in this model. We have solitons and vacuum. So the electric and magnetic fields are like in the vacuum perpendicular to each other. This is, of course, also a question which one has to check. There exist non-quantized magnetic currents, I told you, but if the energy is minimized, they should be also minimized, and they have no influence on Lorentz and Coulomb and Lorentz forces. There are alpha waves which I can't attribute to dark matter contributions. They may lead to additional forces on particles and could lead to quantum fluctuations. If such alpha waves hit on some soliton, it could shift its place, and this could correspond to the quantum fluctuation in the path. I told you the potential term is a mechanism for cosmic inflation, and the potential term a contribution to dark energy. So, some aftermath. Physics is measurement of distances of objects and times of events. This may indicate that physics is geometry and not algebra. We should use the algebra to describe the geometry, not the algebra by itself. There's a famous saying by Wheeler: space-time tells matter how to move, matter tells space-time how to curve. I can add to this: charges and rectangular fields tell space how to rotate. Yes, no model in our science is final, because we have still big puzzles, and as long as we have big puzzles, no model is final. So this is a model where everything is finite. This you can extend by yourself. Thank you very much.
Thank you very much for your talk. So do we have questions regarding the presentation of Professor Faber?
Yeah.
Maybe I have one question. There is existence of fractional quantum Hall effect. There is a quantum Hall effect and fractional quantum Hall effect. In the fractional quantum Hall effect, there is disattachment of spin from charge, which is observed in condensed matter system. Also, it happens that electric charge is quantized. It can be 1/3 over times electric charge of electron, or 2/3 times electric charge of electron. So does your theory can tackle with description of such effect, quantum Hall effect?
This is, of course, a very interesting problem, and I was thinking a lot about this, but I have no real answer to this. of course, this looks also, this non-integer quantum Hall effect looks, of course, also very topological, and but I cannot connect it with my model. Sorry.
I see. All right.
Pity, but
Yeah, so let's say if somebody is experimentalist and wants to verify your model, does your model predicts any type of extra phenomena that shall be observed but was not yet observed?
it's the next question, right? It fits very well to all this phenomena of electromagnetism, and it's not really something which predicts, different. I mentioned it. Of course, you have such phenomena as cosmological constant, it's just very many features, as I explained. But it's not really something which you can say it's a new prediction which one should check. It's really a pity, but I didn't find anything.
Yeah, but let's say, but you produce the same equations of motion as quantum mechanics does, right? Standard quantum mechanics does, right? Can you say in that way?
No, it's a classical model first.
It's classical model that reproduces quantum mechanics from certain perspective, right?
If I do these steps which I have indicated with the Dirac equation, then of course you somehow go to quantum mechanics, but it doesn't explain quantum mechanics. So I have to examine the existence of vectors in Hilbert space. I have to accept canonical permutation relations. This means that the momentum is written as a gradient. It's formulated as gradient. So it's not really, there's no derivation of quantum mechanics. So it's a simple classical model. It's really simple because it has only 3 degrees of freedom and a very simple Lagrangian.
Yeah, because let's say, you know, those days qubits and quantum computation is very fashionable topic.
Yeah.
And the question is there a chance you use another classical language to describe qubit operations? So would this language proposed by you would be efficient or not?
I suggested to investigate these liquid crystals because they have the same topological objects. So the electric field in my model is represented as a rotating field. So it has curvature. So it's curvature on S2. It's an electric field. So you have to have something. You have a field of such vectors which have a curvature, and this curvature, this gives you, if you have a constant electric field, you can only produce it with something which is rotating. And if you look at these liquid crystals, they have a perpendicular electric field. And this perpendicular electric field, if you look in some of these figures, it rotates. It looks as it rotates. So Jarek suggested, and possibly we do, that we compare this with liquid crystals, and we can find if we can explain liquid crystals in this way.
I see. So this language proposed by you has potential use in the liquid crystal physics description, something like that.
Like this, it's the same phenomenon. They have topological objects. You see, they compare it with the Stern model, which is very close. And so of course, my model in this sense is better fitted for liquid crystals because I can treat charges. Whereas the topological solitons of the Stern model, they have short-range interaction and not Coulomb interaction. In the liquid, of course, you have objects, dipoles, which have Coulomb interaction.
I see. Yes.
Yeah.
All right. Sounds good. Do we have any more questions for the speaker? All right. If not, thank you, the speaker, again, and thank you to every speaker of the day. And see you tomorrow on another sessions. So there will be tomorrow and day after tomorrow. Tomorrow is more oriented towards computer science and machine learning, but still there will be like a quantum Conway game of life. So that's my joint work with my student, so that just defended his Master of Science thesis with distinction. Professor Gnatenko will open a session about quantum computer science, but she's a physicist, so please attend talks tomorrow. And on Friday, there will be some talks about quantum electronics. and also single photon detectors, and also there will be one mathematician talk on a Friday. Actually, two mathematician talks on Friday. So please recheck the schedule, which is on the webpage hypercomplexseminar.com.
Does the discussion section take place tomorrow?
Yes, I guess so. Professor Dr. Michalski, tomorrow we have a discussion section, because actually if there's a such, maybe we can also continue until, since we have no more barriers today, so if there is a need for discussion, we can have it straight away right now, if there is but tomorrow is scheduled, discussion is scheduled at
14. 2 p.m.
2 p.m.
2 p.m.
14.
Right.
Yes, it's 2 p.m. But please check the program in the morning.
Yeah. Okay.
Because there is always a possibility that some changes may appear. So strongly recommend to check the program each morning.
Okay. Thank you very much.
Thank you.
Yeah, I guess yeah. So Professor Faber, do you see the opportunity for discussion now, or you prefer to postpone till tomorrow?
We had a discussion, so it's not important. So,
yeah, well, I guess we are a little bit overloaded since we run from 10 o'clock pretty much, right? So yeah, so yeah, so anyway, I have to still to read the I mean yeah, that's quite intensive
it was
stream of facts and implications as given from your talk, so I have to take those arguments step by step to see things, you know.
Because I was only asking because there was announced for tomorrow a discussion panel at 2 o'clock, and when my name was there indicated. This was my question.
Yeah, so I mean, you're really yes, you are chairman of this discussion session, so it would be nice if you would be present. Yeah.
If I said this, no problem.
Yeah, and yeah, right. So thanks.